In this video, we'll revisit the optimality conditions for linear programming, and in particular, we'll show how they can be derived using the Farkaslemma. So let's consider an LP in the form minimize C transposed X, subject to AX is greater than or equal to B, X is greater than or equal to 0, and let's denote by X capital the feasible region as usual. So we have the set of X's that satisfy our constraints. Now assume that X star is an optimal solution to our problem. So our feasible region is defined by what we call the defining hyperplanes that come from these inequality constraints as well as non-negativity. In particular, an inequality from this part of the system is given by AI transposed X is greater than or equal to BI, where AI transposed is the ith row of the matrix A, and the BI is the ith entry of the vector B. And then an inequality corresponding to non-negativity can be described as EJ transposed X is greater than or equal to 0, where EJ is the vector that contains 1 as the jth entry and the rest of the entries are equal to 0. So essentially this is the same as to say that Xj is greater than or equal to 0. Now assume that we know which of the inequalities in this system are satisfied at equality at X star. So we are going to separate binding and non-binding constraints, including the non-negativity constraints, in this system. So we are going to write our system that combines all of the inequalities, including non-negativity, as GH multiplied by X is greater than or equal to G small h small, and here G capital represents the left hand side of the combined matrix of this system that represents the binding constraints at X star, and then H does the same for the non-binding constraints. So essentially this means that if we consider G times X star, then it will be equal to G small, because again the upper part of this system corresponds to the binding constraints, and then H times X star is strictly greater than H, because this part of the system corresponds to the non-binding constraints. Now the fact that X star is an optimal solution to our problem means that whatever feasible direction at X star we consider, the objective function cannot decrease along that direction, because if it did, this would contradict to the optimality of our point X star. So now how do we describe feasible directions for our point X star and the feasible region X in terms of this system that we have written here? So to determine the feasible direction, we only need to pay attention to the binding constraints, because there is some space for us to move along any direction with respect to the non-binding constraints, right? So for binding constraints, we need to make sure that G times D is greater than or equal to 0 for the direction to be feasible, because if it is greater than or equal to 0, then G times X star plus alpha D, where alpha is some positive step size when we move along the direction D, is gonna be equal to, first of all, G times X star is equal to G small, and then plus alpha times G times D small. And this is going to be greater than or equal to 0, because GD is greater than or equal to 0 and alpha is the positive step size. So this will ensure that the inequalities in this system are still satisfied. And we can also easily show that if GD is not greater than or equal to 0, then the direction D is not going to be feasible at the point X star. So all feasible directions at X star are described by D's such that GD is greater than or equal to 0. So now the fact that X star is an optimal solution, as we said, means that for any feasible direction, the objective cannot decrease. So which means that if I write down the system GD is greater or equal to 0, so this represents the feasible directions, right? And then C transposed D is less than 0, which represents the fact that the objective will decrease along this direction D, then this system does not have a solution. If it did, this would mean that X star cannot be an optimal solution, right? Now, applying the Farkaslemma, we conclude that the system G transpose times Y is equal to C and Y is greater or equal to 0 does have a solution. So this already gives us a necessary optimality condition for our linear program, because we have proved that if X star is an optimal solution to our LP, then for the matrix G corresponding to the binding constraints of our system here, we must have Y that satisfies this system right here. In order to be able to use this condition, we need to express it in terms of our problem data here. For that, what we are going to do, we'll define the set of indices for the binding constraints as I capital. So this will be the set of i's for which AI transposed X star is equal to B. So this will correspond to the rows of the matrix G corresponding to the entries of this part of our system AX greater or equal to B, right? And then we will also define the set of indices for the binding constraints for the non-negativity constraints, right? So J will denote the set of J's such that EI transpose times X star is equal to 0, which is the same as to say that XJ is equal to 0, right? So then the rows of G, our matrix corresponding to the binding constraints, will be given by AI transposed for I in the set I and by EJ transposed for J in the set J capital. Now for this vector Y in this system, we are going to distinguish between the entries of Y that correspond to the rows of matrix A and the entries of Y that correspond to the non-negativity constraints. So we will represent this vector Y as a combination of UI's and VJ's. So essentially our vector Y will be consisting of vectors U and V, where the vector U will be of the length corresponding to the power of this set I, and the length of V will be given by the power of the set J capital. So now, using these new notations, we can rewrite our system as follows. So you have G transpose times Y. Now for G transpose, the columns will consist of AI's and EJ's, right? And then the entries of Y corresponding to the columns given by AI's will be given by UI's, and the entries of Y corresponding to the columns given by EJ's are VJ's. And as a result, we can now write this part of the system as follows. So it's gonna be the summation for I in the set I capital of UI's AI's plus the summation for J in the set J capital of VJ's EJ's, and this is the left hand side of our system now, and this is supposed to be equal to C. And also we have the non-negativity of Y's, and Y's consists of U's and V's. So we have UI's are greater or equal to 0 for I in the set I, and VJ's are greater or equal to 0 for J in the set J capital. So this is our necessary condition here. So if X star is an optimal solution to our LP, then there must be the multipliers UI's and VJ's that are non-negative, such that if we consider this summation over the active constraints at the point x star, then it's going to be equal to C. So we have established that this is a necessary condition for optimality of x star, but we can also show that this in fact is a sufficient condition for optimality as well, making it both necessary and sufficient condition. So to show that this condition is also sufficient, let's consider an arbitrary point x in our feasible set, and let's consider the difference between C transposed x, the objective at point x, and the objective at the point x star, which is C transpose times x star. Now we assume that this condition is satisfied, and we need to show that x star is the minimizer for our problem, right? So using this condition, C transposed x minus C transposed x star corresponds to multiplying the transposed of the left-hand side of this equation by x minus x star, right? So it's gonna be the summation of ui's ai transposed times x minus x star plus the summation for j's of vj's ej transposed times x minus x star. Now we know that ai transposed times x star is equal to b, and then ej transpose times x star is equal to 0, right? So taking this into account, we can rewrite this expression as the summation of ui's times ai transposed x minus b and plus the summation over j's of vj's ej transposed x. Again, ej transposed x star is 0, right? So this part disappears, and this is what we have here, right? But now, because x belongs to x capital, this means that ai transposed x is greater than or equal to b, meaning that this is greater than or equal to 0, and everything else is greater than or equal to 0 here as well, because due to feasibility of x small, again, this is greater than or equal to 0, and from our condition ui's and vj's are non-negative as well. So as a result, we have the whole thing is greater than or equal to 0, meaning that for any feasible x, C transposed x is greater than or equal to C transposed times x star, implying that x star is the optimal solution. So this proves that this condition here is the necessary and sufficient condition for optimality of x star. The optimality condition we just established is known as the Karush-Kuhn-Tucker optimality conditions, and these conditions actually are applicable to more general problems in nonlinear optimization, and what we see here is just a special case of the KKT or Karush-Kuhn-Tucker optimality conditions applied to a linear program. So this is again the condition that we developed, and next we'll look at the geometric illustration for these Karush-Kuhn-Tucker conditions. Geometrically, just like with the Farkaslemma that we discussed before, the condition means that the gradient c of the objective function belongs to the cone defined by the gradients of the binding constraints that are given by ai's and ej's. So let's consider an illustration of this condition for the problem that we solved before geometrically. So what we do here, we put this problem in the minimization form so that it corresponds directly to the optimality condition the way we established it. So we multiply the objective by -1, and then we reverse all the constraints to greater than or equal to constraints. Then if we look at the optimal point C here, we can see that the gradient for the objective function will point in this direction right here. So this is going to be the direction of increase of our function, right? And then if we plot the gradients for the binding constraints, and for this constraint right here, the gradient is going to look like this. And for the other binding constraint, which is the budget constraint, the gradient is going to be orthogonal to the level set, and it's going to look roughly like this, right? So this is supposed to be orthogonal to this line, just like this one was orthogonal to this line. So we can clearly see that if we look at the cone generated by the gradients of the binding constraints, then it's going to look like this, and clearly the vector C, the gradient for our objective, belongs to this cone. So the optimality condition is satisfied at this point, and this is how we can tell that this point is optimal for our problem. On the other hand, if we look at a point like this one, point F right here, then we can see that the cone generated by the gradients of binding constraints will look like this. So we have the gradient for the demand constraint is something like this, then the gradient for the active non-negativity constraint will look like this here, and the cone generated by these two is going to be here. And at the same time, the gradient for the objective will point in this direction, and clearly it doesn't belong to this cone. So this point cannot be optimal because it doesn't satisfy the optimality condition. Okay, we developed the optimality condition in this form right here, and in order to be able to check this condition, we need to know which constraints are binding at the point that we are considering, right? But what if we ask the question, given a linear program, find a point that satisfies the optimality condition? Then in this case, we don't really know which constraints will be binding or non-binding at our point, and we need to be able to address this question as a part of our optimality conditions. So for this, what we are going to do, we'll develop what we call the complementary slackness conditions, something that we are already familiar with, but now we are going to obtain these conditions based on this system that we have here. So since we don't know what set I is going to be, what we are going to consider is the summation of ui's, ai's for all i's. And assuming we have m constraints, it's going to be for I between 1 and m. And then we are going to consider this summation of vj's, ej's for all j's. And assuming we have n variables, we have this summation here, and this is supposed to be equal to c. But now we need to make sure that whenever the constraint is non-binding at the point that we are considering, then the corresponding multiplier ui is equal to 0. And similarly, whenever non-negativity constraint is not satisfied at equality, we have to have vj equal to 0. And the way we can express this, we can just say, all right, ui times ai transposed x minus bi is equal to 0. So whenever the constraint is not satisfied at equality, this will be strictly greater than 0, and as a result this will force ui to be equal to 0, which is exactly what we need, because again, this sum right here is supposed to include only the terms for the active constraints, right? Similarly, for the non-negativity constraints, we need to make sure that vj multiplied by xj is equal to 0. And this is supposed to be for all j's between 1 and n, and I between 1 and m. So in the case of the non-negativity constraints, we see that whenever xj is positive, vj is forced to be equal to 0, which is again exactly what we need. Now, observing that both ui and this difference here are non-negative, we see that the product will be equal to 0 if and only if the summation of such products over all i's is equal to 0. So you have the summation of ui's ai transposed x minus bi must be equal to 0, right? So this is for all i's between 1 and m. Or in the matrix form, this is equivalent to saying that u transposed multiplied by ax minus b is equal to 0. And looking at this equation here, vj's times xj's will be 0 for all j's if and only if the summation of vj's xj's will be equal to 0 for all j between 1 and n. And we can represent this as a scalar product v transposed x. Also note that this system right here can be written in the matrix form as A transposed U plus V is equal to C. Alright, so this is equivalent to what we have here. And now we are ready to state the KKT optimality conditions in their more common form, including the complementary slackness, primal feasibility, and dual feasibility. Alright, so we'll start with the primal feasibility. So when we write down the Karush-Kuhn-Tucker conditions, first of all, we need to make sure that our point for which we look at the optimality conditions is feasible, right? So the primal feasibility is given by this system here. So ax is greater than or equal to b and x is non-negative. Then we write down this equation right here that we developed. So we have A transposed U plus V is equal to C, and both U and V are non-negative vectors. So, and this is nothing else but dual feasibility actually, because look at this system here. So you have A transposed U is less than or equal to C is nothing else but our dual constraint for our LP. Then we add the slack variables given by the vector V and we obtain exactly this system right here. So together with non-negativity of the dual variables, we obtain the dual feasibility condition. And finally, we write down complementary slackness in this form right here. So we have U transpose times AX minus B is 0 and then V transposed X is 0. And this summarizes our optimality conditions. If we write down the optimality conditions for the equality constraint case when AX is equal to B, then in this case our dual variables U's will be unrestricted in sign, and also AX will be equal to B, right? So which will make this complementary slackness condition automatically satisfied, and the only part that will remain for complementary slackness will be V transposed X equals 0. As a result, we obtain the following optimality conditions in this case. So for primal feasibility, we have AX is equal to B and X is greater than or equal to 0. For dual feasibility, it's A transposed U plus V equals C, and then U is unrestricted in sign, and V is greater than or equal to 0, and complementary slackness is just V transposed X is equal to 0. Let's see what happens to the optimality conditions when we consider a basic feasible solution that we have during the execution of the simplex method. So in a basic feasible solution, we have Z equal to CB transposed B inverse times B small plus Cn minus CB transposed B inverse times N times Xn. So that's row 0. And then we have XB given by B inverse times B small minus B inverse times N times Xn. And recall that we obtain the basic feasible solution by setting Xn to 0, then XB will be equal to B inverse times B, and so on. Let's see when the optimality conditions will be satisfied at a basic feasible solution. So first of all, primal feasibility is something that is satisfied for any basic feasible solution. So we have XB, the basic variables expressed through the non-basic variables in a way that AX is equal to B, all the variables are non-negative, so the primal feasibility is there at any basic feasible solution. Now, how about complementary slackness? So let's look at complementary slackness ahead of the dual feasibility. So for complementary slackness, we have V transposed X equal to 0. So let's break this down into basic and non-basic variable parts. So we have V transposed X is equal to VB transposed times XB. So here VB will be the part of the vector V that corresponds to the basic variables, then plus Vn times Xn, and all of this is supposed to be equal to 0 according to complementary slackness. So here, of course, Vn would be the part of vector V that corresponds to the non-basic variables. And then recall that in the basic feasible solution we have Xn equal to 0, therefore this part will disappear, and we have, for complementary slackness to be satisfied at the basic feasible solution, we need to have VB transpose times XB equal to 0. And of course we can obtain this by just setting VB equal to 0. Once we have this assignment, obviously this condition will be satisfied and complementary slackness will be satisfied. Alright, so now how about dual feasibility? For dual feasibility we have A transpose U plus V equal to C. So what we're gonna do, we'll write down the dual feasibility condition also by splitting the basic and non-basic parts in this system right here. And to make it more convenient, what we're gonna do, we'll look at the transpose of this system. So it will look like this. So you have C transposed is given by U transposed times A plus V transposed. And now we are splitting everything into basic, non-basic parts. This will be equivalent to, we have CB, CN, all of this transposed, equals to U transposed, then the matrix A will consist of B and N. And then V transposed will consist of the basic and non-basic parts. So we'll have VB and then Vn. Of course, both transposed. So recall that our VB was set to 0 in order to satisfy the complementary slackness. So when we set VB to 0, here is what we get from this system here. So let's write the basic and non-basic part separately. So we'll have CB transposed is given by U transposed times B. And then from this part we have plus VB transposed, but recall that VB transposed is 0. So this is it for the part corresponding to the basic variables. And then for the part corresponding to the non-basic variables, we have Cn transposed is equal to U transposed N plus Vn transposed. So we need this system to be satisfied for dual feasibility, and we can compute U transposed from the first equation by multiplying both sides by B inverse from the right. We know that B inverse exists because we are talking about a basic feasible solution here, and we have U transposed is equal to CB transposed B inverse. And now we can plug in U transposed into the second equation to compute Vn transposed. So Vn transposed is given by Cn transposed minus U transposed N. We replace U transposed with CB transposed B inverse and then multiplied by N. And this is our solution here for the dual variables in order to ensure the dual feasibility. We know that U is unrestricted in sign, so this here works to satisfy the condition for U, but then v is supposed to be greater than or equal to 0. We know that vb is equal to 0, and we need to make sure that vn transposed is greater than or equal to 0 in order to ensure the dual feasibility, which was the last condition we needed to satisfy in order to have the basic feasible solution satisfy our optimality conditions. So now we have this condition that we need to satisfy, right? And looking at what we have here, so Cn transposed minus Cb transposed B inverse times n is exactly what we have here in the basic feasible solution in row 0 of it. So this is the coefficient for the non-basic variables, and we know that the non-negativity here is what we require in the simplex method optimality condition. So this was our stopping criterion for the simplex method. So essentially what we used in the simplex method was the optimality condition that can be thought of as the Karush-Kuhn-Tucker optimality condition, so where we have this complementary slackness and primal and dual feasibility satisfied, and we would stop as soon as our basic feasible solution satisfies this condition. So dual feasibility is the same thing as primal optimality in the simplex method. And as we can see, at every iteration of the simplex method, we have primal feasibility and complementary slackness automatically satisfied by the design of the simplex algorithm. And then we keep going until we also satisfy the dual feasibility condition. And as soon as we reach the dual feasibility, we stop and conclude that the solution that we get with the simplex method is optimal.